Hi all, this is a very warm community here in Bangalore. We kind of miss this in Hyderabad. The database community there is not as large as what I see here. So that's one reason, despite a medical emergency, I had to quickly rush the slides. So please pardon me if the slides are not in the best shape. Saying that, one of the teams that I manage at Ninja, that's our data team. We have both transactional and analytical as part of our team. And I'm going to briefly just share the journey that we've gone through in the last 10 years. How did our data scale and what kind of challenges did we experience? What prompted us to start looking at the next generation of databases? Okay. All right. So we are Ninja Band. We are the last mile logistics in Southeast Asia, equals to Shadowfax, delivery, and what else is there? E-commerce, Commerce B in India, something similar. But in Southeast Asia, we are in 6 countries. We started in Singapore and we expanded across Southeast Asia over years. And we are in 6 markets, Singapore, Malaysia, Indonesia, Philippines, Vietnam, Thailand, with 100% coverage. We started in the year 2014, and then 2015 was Malaysia and Indonesia. Following year, the rest of 3 countries. So some of the well-known names of our shippers in Southeast Asia, Amazon, Lazada, you guys must be familiar with some of the names here. Right, so briefly going through our tech stack. So we've been multi-cloud mostly. We started off with AWS, then we are on GCP. We are also a little bit on Ali Cloud. We are on Huawei. Most of our workloads are containerized. They are kube native. We are completely on Kubernetes. And our databases, our journey started off with MySQL mostly. Now we are moving mostly towards TiDB. Caching, Hazelcast, mostly moved to Redis. Event streams, Kafka mostly. Backend started off with as a Java shop, then we are now into Golang mostly. Monitoring, logging has been pretty constant since the start. Kibana, Elasticsearch, Prometheus, and Grafana. And big data, we've started expanding into OLAP scalability issues in the year of 2019. That's when we started mostly on Spark. Right, so this has been our DB journey. 2015, we already started containerizing in production, right? So before Kubernetes, there was Fleet, and we first played around with Docker in production. That was on Fleet, and then Kubernetes dominated completely. So 2016, Fleet recommended to migrate over all of its users to Kubernetes. That's when we had an on-prem Kubernetes that we deployed. We were managing it ourselves. However, MySQL databases were still on VMs mostly, right? So there is always this taboo that deploying databases on an ephemeral cluster. It sounds a bit scary, especially if you've been operating on traditional VM instances. So we've been mostly MySQLs have been on VMs, and coming to the database tooling. We started off with Percona Toolkit mostly. That was the most mature back then, whatever we had. So PTOSC was our bread and butter for all alters. Right? Of course, it's a trigger based, so there are certain challenges for PTOSC. Hence, eventually, we replaced Percona Online Schema Change with Ghost. So Ghost was by GitHub, right? And it gives you more controls, particularly if you have a complex replication topology. You need to control the replication traffic. You need to throttle it based on certain parameters, CPU, memory, right? So we had those controls. I mean, nowhere close to what DXF offers, but I think back then that was one of the feasible solutions that we had. And of course, PMM monitoring, the first love for DB monitoring, still in production for MySQL. So fast forward from 2016 to 19, we've been pretty much on Percona ExtraDB cluster. Galera cluster was our transactional database mostly. we started experiencing write scale bottlenecks in the year of 2019, 2020. Hence, we had to resort to a stopgap measure for about a year while we were deciding which is the best distributed database solution that we could move forward with. Right, so that's when we started exploring alternatives for addressing our write scaling bottlenecks, and that was the humble beginnings of TiDB 4. Right, so 21 to 25, sorry, my slide is not fully updated. Together with TiFlash, we've also migrated TiDB 5 to version 7 and then 7 to 8. Most of it was TiDB operations. Right, so 16 to 19, what were we on? We were MySQL binary with Galera plugin. This was more for the replication setup, for the multi-master replication setup that we had. So the pros, obviously, it's easily read scalable. If you need to scale up your topology, you add in a new node. Of course, there are some performance problems to it. As soon as you add a new node, you have a state snapshot transfer that gets triggered, and there are certain performance implications to it. And the most important problem, it is not really fully write scalable. We've experienced a lot of flow control problems. If you guys have, any one of you guys have worked with Galera particularly, upon high write traffic, especially if the nodes are choked up on resources, you start experiencing write bottlenecks, right? So your commit starts to slow down and you start seeing a lot of performance issues. Hence the stopgap measure. Once we started seeing these performance issues in production because of the quick growth that we've experienced, as a stopgap measure, we started resorting back to Pocona server, and we were using proxy SQL as a means to temporarily aid us with some of the challenges that we face, particularly with consistent reads, right? So let me just briefly show you guys how the configurations that we used to configure. So you can see the query rules that we've configured here. Most of these rules are managed by the DB ops team itself, right? So you can see for critical reads particularly, we are doing a sort of a regex within the SQL query. So the downsides to this, you're again moving a lot of this logic over to the application code base, and you have to maintain all of that. And even if you look at the way we've handled sharding, all of these sharding rules start to become very complicated, but we knew it. We knew that these were the downsides. We were just using it as a stopgap until we quickly figure out either, we go with Vitess, which was also something that we've explored, which I'm going to talk about in the subsequent slides. Now, while this was the transactional processing side of our functions, there was also a bigger problem that was brewing. With the quick growth that NinjaVan has gathered with respect to the data needs, we started experiencing bottlenecks and choke points on building products for our operational intelligence users. So a quick solutions, all the ops users, they are comfortable with SQL, so they've asked us a solution while they wait for the product builds to be shipped out quickly. And something that we thought of, which is not a very clean solution, but we exposed some of the operational data to them that is needed in the form of MySQL slaves, right? So this is what I refer to as the mid OLAP. It's not really fully OLAP because the nature of data here is not completely analytics. There is data retrieval, you're doing lookups, sometimes you're pulling out specific rows within a table. So it's not completely just for aggregates, right? So this makes it very challenging for us to pick one particular data solution because you cannot educate the users that, okay, you have to use a different database for a specific set of SQL queries. All they're aware of is what's their operational use case, and they come up with a very complicated SQL query that includes a little bit of lookups, a little bit of analytics, and that made it a little challenging for us. So most of our business intelligence and operational intelligence at this point of time in this period was powered by MySQL slaves. It's a cluster of slaves. We've set up certain automation for it to scale up, scale down. So there was a lot of automation around DB operations. So that's to support the agility and sudden growth. And we also have employees who are very comfortable with SQL, quickest way to do the business operations without waiting for product, need for near real-time data plus aggregates. And all they needed was a front-end tool, an open source one, Redash or Metabase for them to query an back-end array of sleeves. So this was our initial ODS architecture that survived for 4 years, surprisingly. So the source masters, which are MySQL, we set up a multi-channel replication to a single ODS. And very clearly in the architecture, you can see the choke point is in the multi-tier one. What if the microservices start scaling up, right? Whether the traffic can be handled there. We've used very selective filters for these multi-channel setups. So we were regulating the traffic that goes into the tier one ODS. So that helped us for about 3 years. And the tier two is basically the worker nodes, which is an auto-scaling group that we have configured, and we expose this workloads to the users through a proxy SQL that is basically fronting the Redash. Right, and then what happened? In 2020, 5 years after we've deployed this solution, we started seeing very, very complicated SQL queries, 900 lines of SQL queries that users keep bombarding the DB clusters. No matter how much of metal you throw into that auto-scaling group, it was not really working out for us. I don't have an explain plan for the MySQL, so I've taken one for what we have today, which is a TiDB cluster. And you can see from the explain plan, that's about 46.3 mil, right, approximately? Yeah. So you can see these queries can get quite complicated, and it is absolutely not possible that we run them on the MySQLs. It is impossible that they'll work. They're going to consume all the resources and they're going to time out. And the timeout settings cannot be as aggressive as what we configure on transactional, because some of these queries indeed take 2 minutes or 3 minutes. So these were the challenges, right? 900 lines, SQL queries, improper indexes, full table scans, wildcard searches, very insistent demand for complex reporting needs, and they need real-time or close to real-time expectations of data availability. And there were also expectations of query performance, right? So they needed these queries to complete within under a minute. And Redash became a necessary evil, right? It did help us very aggressively scale up our operational dependency on data. And but yeah, we were facing a lot of challenges, right? And we tried adapting the existing architecture by addressing some of the challenges that we noticed. If you see, we've introduced another tier, a 3-tier architecture became a 4-tier architecture, and we've introduced bin log relay servers to reduce the load on the multi-channel tier 1, right? So there were a lot of replication lags that were causing the data to not be available in the specific SLAs that the ops teams needed. And now auto-scaling started growing to 100 servers, right? That was not sufficient enough. We moved from an SSD to a local SSD setup. We started regulating the data that goes into these slaves to facilitate better query performance. And we also started noticing proxy SQL performance bottlenecks as well, right? And moreover, particularly when there's database migrations that run on masters, you do have a lot of downstream replication impact to it, right? Because now you're running alters on 3 terabyte tables, 4 terabyte tables. It generates a lot of traffic, and that starts to become a choke point everywhere downstream. While Ghost has very good controls in regulating the migration depending on the downstream lags, but it was still impacting our operations. So we started looking at all the requirements. We've experienced 2 problems, one on the transactional processing, write bottlenecks, and on the analytical or operational data store, where we started experiencing replication lags, we started experiencing queries not functioning. It was very hard to maintain all of this operationally. So primary MySQL compatible because we already had about 60 to 70,000 queries, and migrating all of this just for Redash or just for the operational data store was challenging, right? And of course, on the transactional processing side, we had about 180 microservices, and if we decide any particular technology change, that will be a very, very long running migration effort for us. So that was primary, that was a mandate. It had to be MySQL compatible, at least most of it. And easy operations, we needed both read and write, scalable, highly available, CDC core of it, because we started setting up our big data lake, the data lake architecture, and also CDC was an essential component on the transactional processing. And of course, monitoring, and of course, Kube native is always the best. So what did we explore? So we explored Ali Cloud, ADB, we explored GaussDB, which was on Huawei, and of course MySQL HeatWave. And on the open source, Vitess, we've looked at Cockroach, we've looked at TiDB. Right, and that's when I think we started playing around with TiDB, humble beginnings, version 4.0.7, we started just deploying small clusters, scale up, scale down, how do we take backups, right? Everything was a breeze. We had a lot of manual tooling that we custom built in-house with respect to our MySQL clusters. But with TiDB, a lot of this was already catered to as part of the ecosystem. So ODS was a perfect case study, or a guinea pig for us to test hybrid workloads. And it's slightly less critical for us. We could take a shot at it. Once we are confident, we thought that we would plan to adopt it on the transactional processing as well. So Redash, not a very large data set. If you can see, it's about 25 terabyte. Traffic varies from simple data retrieval to complex analytical queries. Supports 10,000 plus users. We needed very strong resource control setup because this common cluster was shared amongst all the countries, right? So all these 10,000 plus users were running from various locations, and we needed to be able to regulate and control how much capacity of the cluster can each country utilize, so that we avoid the noisy neighbor problem, right? So that one country doesn't impact the cluster workload. And TiFlash was something that perfectly fit this use case. So when TiDB has this smart logical routing layer that decides whether this query executes optimally on TiFlash, whether it should, right? So and this is also a guinea pig to test any new TiDB upgrades. So this is how we've been keeping ourselves up to date on TiDB upgrades. We first tested out on this cluster, and if things go well, then it goes to production on the transactional processing. Right, so this is briefly the architecture of our operational data store. So we do have MySQL. It is an incremental migration, and maybe some of the workloads they might be too less of a bottlenecks for us to even consider deploying them on TiDB. Very minimal workloads, right? Internal tooling, internal databases. So MySQL data also needed to be there on the TiDB cluster. So that was our consolidated data solution. So we set up replication through DM, part of the part of the TiDB ecosystem, and all of that data was consolidated in the TiDB cluster, and this was served through all of our visualization solutions and any other data intense applications. Okay, so OLTP from 21 to 24. I think this is something that that were the core for us, right? Full MySQL compatibility, or most, at least, and it had to be horizontally scalable, highly available, everything standard, right? All the speakers have spoken about them, so I'm gonna briefly skip. Okay, yeah, DDL is a breeze in TiDB, right? So no ghost, no PT, online schema change, very minimal impact on downstream replication lags whenever we run DDLs. And resource control is something we never had before. The way we do resource control last time was doing the logical partitioning of the MySQL clusters. So the database operations teams decide which workloads to go where, and this often results in ineffective utilization of the resources. So you do have clusters of 100 MySQL instances where you see pockets of free capacity all over. So resource control was something that we really had our eyes on. As soon as it was launched, we really upgraded all of our TiDB clusters in production. And cloud native, our CI/CD and infrastructure as code for managing all of the databases that was in bits and pieces in Ansible, in various other, Amazon's equivalent of Terraform. There's something, right? So we've had bits and pieces everywhere, and we've consolidated all of that into very good Terraform, TerraGrant, Kube Manifest, and of course open source, right? So summary, what we love in our experience, 54K QPS, so we process more than 3.2 million queries every minute, right? And there was a particular incident where we had a very brief period of outage for TiCDC, and we noticed that as soon as we brought it back up, the recovery was amazingly fast. And backups, last time for backups, we used to have a lot of manual scripting, and we used to store all of these backups in S3, a lot of in-house scripting and automation that we've done. So everything pretty much seems out of the box. TTL, archival is always a challenge in MySQL, right? Because when you run archival, you have to take so many considerations downstream. Replication lags will be there, whether these events are being processed properly in your downstream data analytics stores. So TiDB gives us out of the box TTL controls and all of this. The impact is very minimal, and of course, again, credits to DXF. TiFlash, the real-time analytics use cases of Redash of the operational data store that I've shared, I think that's something that we also aggressively use. Resource control, which is the best, right? So future, what are we looking forward to? So ARM migrations, we've noticed significant cost savings with ARM setups. So if TiDB clusters are heavily running on Intel or any other chipsets, I think ARM chipset seems like something that the industry is moving towards. Migration tooling, of course, for cluster operations from MySQL to TiDB, I think a lot database related. And 180 plus microservices and growing, 44K peak TiDB QPS, 130 terabyte of data growing at 200 GB per day, and 30 terabyte is our largest table. Right, so the awesome team behind this work, I think we have a 20-man team based in SG and IN. I'm just kidding, it's not 20, it's just 2 of them. That's Kat. She heads our data infra team, and Srikanta is also here with me. So again, special shout out to PingCAP team. I think without their special care and support that they've given us, there have been days where we've reached out to them on GChat, on Slack, and then we immediately had new Docker images pushed out in the next 2 days. So I think the spirit of agility has been there since day one. And of course, documentation is awesome, right? So we love PingCAP's documentation. Yes, and shameless plug. We are hiring, so if there's a link there on the deck that links you guys to our Medium blog post, and you can read some of the fun stories there. So please do join us, right? And thank you.